so the divergence and the curl, they both rely also in this del operator. So again, we're going to go back to take a bunch of partial derivatives. So here is the thing. For the divergence, and this divergence operator that we just looked at in the second version for Green's theorem, uh, if we think of this quantity that I highlighted in green in a backwards way, we can see a dot product going on. How come? Well, that's because, yes, because in this case, this nabla operator dotted with some vector field in this case, where the nabla operator is the partial derivative operator with respect to x, comma, the partial derivative operator with respect to y. These are not yet derivatives. These are just operators, instructions to act on functions. And at the same time, you might recall that this big F, this vector field is some function f, some function y. So take the dot product between those two vectors, and this is going to be indeed the divergence. The divergence of the vector field. All right, and of course we can extend this in 3 dimensions, and the divergence denoted div f, that's divergence. That's essentially the partial derivative with respect x of f of the f component with respect x, plus the partial derivative of the g component of the vector field with respect to y, plus the partial derivative of the h component of the vector field with respect to z. I think it's pretty straightforward that we go in order and also in alphabetic order when we do the dot product of these two vectors. And one thing to recall as well is that the dot product gives us a scalar as opposed to the cross product, which gives us another vector. Well, that's going to be the curl later. But for now, let's look at the divergence. And the divergence, what is this anyway? It measures the expansion or the contraction of a vector field at a given point. And in the situation in which the divergence is 0, that means that at that point, or rather the vector field is source free. So it's neither a sink nor a source. All right, so it's just source free. And so in this, the illustration next to it, so this is illustrating, points in which the divergence is positive. That is, there's an expansion, and points in which the divergence is a compression. So if this point right here, it's compressed by this is being compressed by these two vectors, right? In this case, rather than in this case having an expansion in this case. And so let's see. Let's have a look at one example. All we have to do is find partial derivatives. Find the divergence at 2, 1, -1 for the vector field f of x, y, z equals to x cubed y squared z in the direction of I plus x squared z in the direction of j plus x squared y in the direction of k. All right. So div of f, which is, it's going to be the partial derivative with respect x of the x component of the vector field, that is of x cubed, y squared z, plus the partial derivative with respect y of the component in the direction of j, that is the second component of the given vector field, plus the partial derivative with respect z of the component that goes in the direction of k of the given vector field. That's all we do. So without even setting this as vectors and then do the dot product, we can just take the partial derivatives in the correct order, in alphabetic order. That's all we do. And that's x squared y And let's just take the partial. So with respect x, I guess this is 3 x squared y squared z plus the derivative with respect to y. Well, in this case, there's no y's at all. This is just constant, that's 0. And the derivative with respect to z, there's no z's at all. That's just 0. So in this case, final answer, 3x squared y squared z. All right, but they're asking us to find the divergence at the point 2, 1, negative 1. That is, evaluate div f at the point where x equals 2, y equals 1, and z equals negative 1. That is 3 times 2 squared, 1 squared, negative 1 squared. And in this case, well, simplifying all this, that's going to give us a negative 12. And well, in this case, because of the negative sign, what do we have in this case? Well, it's either an expansion or compression, but based on the sign, we have compression. All right?
The z wasn't square, I don't think.
Yes, that's true. Yep. Thank you. And well, it's pretty straightforward. There's really no trick about it. It's given a vector field, find the 3 partials, and if required, evaluate it at the given point, and well, based on the sign, determine whether we're talking about a compression or expansion. All right? Let's look at curl. The next operator, the curl operator. So, the curl, which is in this case, it's defined in terms of a cross product, not a dot product like we did before. And well, the formula is a little bigger, and I think the formula looks a little familiar from the beginning of the semester when we got the cross product of 2 vectors. And well, so here is the thing, because when I was preparing the class, I was trying to evaluate this 3x3 determinant using the shortcut I showed you of repeating the first 2 columns. However, this time I'm going to use the formula because there's a really big result that will come out of doing it this way. And we're going to relate it to something that we covered back in section 17 point, this is 5? 17.3 or 4, right? 17.3, yes, 0.3. Well, so we're given a vector field f, given by the functions f, g, and h. The 3 functions are differentiable in R3, I mean in 3D essentially. So in this case, we're not going to do the dot product, but the cross product, which is going to be the curl. And again, that's related to the circulation, not the flow out or in, or compression, contraction. So, well, we denote I, j, k, the partial derivative operators on the functions f, g, and h. And notice in this case, the result is going to be another vector, not a scalar like we got in the previous case in the divergence, because again, the dot product is a scalar, while the cross product is a new vector, it's another vector. And that measures the rotation or circulation, and in the case in which curl f equals to 0, the curve is said to be irrotational, so we don't have rotation. It's doing something else. It's going to be some of those vectors that are either going horizontally or vertically, but there's really no. You might remember those pictures we got to see at the beginning of the chapter, in which we have vector fields pointing out and in as a source or thing, and some others rotating, right? So different ways to go. Now, all this, I, j, and k, so we have a particle, right here, that's the particle. So essentially, what this curl is measuring is, so the I component of the curl is giving us the rotation about the axis parallel to I, while the j component is giving us the rotation that is parallel to the j vector, to the direction of j, and similarly for the k component, that's giving us the rotation along or parallel to the k to the k unit vector, right? So that's why we are representing this as a three component vector, because we're looking at what's going on along all these streamlines right here. So we have rotations about all these different axes here. All right, so I guess an example would be great to do. Hold on, no, it's right here. Okay. Thank you. All right, so let's set it up. Yep. So that's I, J, K. So that's partial with respect x, partial with respect y, and partial with respect z. And again, I know I showed you a trick to evaluate a 3x3 determinant by repeating the first two columns. I mean, if you want to do it that way for practice, it's fine. You can still do that. It's going to save you a lot of work, a lot of time. However, there's a big result I would like to show when doing it the formula way. So in this case, well, okay, partial. You know what? Let me write it down over here. Why not? So that's hy, h sub y minus g sub z in the direction of I, minus h sub x minus f sub z into the direction of j, plus g sub x minus f sub y equals to, in the direction of k. Okay, so the partial derivative of h with respect to y, in this case, what's that? 2z. So that's going to be 2z. And the partial of g, in this case, with respect z, what's that? Hold on. With respect to z, rather. It's also 2z, right? In the direction of I. Minus the partial of h, in this case, with respect x, isn't that a 0? And then minus the partial of f with respect to z, that's also 0. And plus the partial of g with respect to x, that's a 2x. And the derivative of f with respect to y, that's also 2x. Did you see how everything gets zeroed out? So what do we get? 0i minus, or either minus or plus 0j plus 0k, essentially the 0 vector, right? Well, what does that mean? So in this case, back from the definition, whenever the curl yields the 0 vector, that means that the vector field is irrotational. Now, let me point something out. I'm not sure what I said before when I was talking. By the way, this should have been on a bold case 0, because that's essentially a vector, right? As a result, as an output, it's a vector, and well, in this case, write an arrow at the top to denote that it is a 0 vector instead of just the number 0, because the number 0, not bold case or without the arrow, means the number 0, and in this case, the cross product, it's another vector, so we're getting essentially the 0 vector. Now, they're asking us another question, whether F is a conservative vector field. So, all right. I would like to go back to the conditions. Okay. So in this case, an interesting pattern to look at is that essentially this hy minus gz, all right, hy minus g z equals to, what did we get for that? Didn't we get a 0? All right? That implies that hy equals to gz. Isn't it one of the conditions for conservative vector field? Second, hx equals hx minus fz. That also gave us a 0, which implies hx equals fz. Isn't that the second condition? And last but not least, gx minus fy also gave us a 0 here, which implies that in this case, gx equals to fy. And it's a third, well, essentially reverse, right? So finding the curl of a vector field is essentially a second way to determine whether a vector field is conservative, because essentially we're making the test. We're finding all these 6 partial derivatives, but in this case we're subtracting them. If we get 0, the 0 vector, well, that means it's irrotational, and therefore it's, in this case, a conservative vector field. So did you see the connection? It's pretty cool, right? All right, so these are the conditions for a conservative vector field. All right. Let's see what's next. Well, I mean, essentially we can formalize this by determining the curl if it's zero. If it's a zero, okay. In this case, I bold case the 0. So it's the 0 vectors. You see, if the output of this operation is the 0 vector, then you have a conservative vector field, and you can do a lot of things with that. You know, if you evaluate an integral over a closed region, going from the initial point back to the same initial point, what's the value of the integral? 0, right? And what else can you do? Find a potential function and evaluate that same. Well, in the case in which it's in an open region, not a closed region, and evaluate the line integral by finding a potential function instead of parameterizing anything. So remember those equivalent sentences that we did at the end of that section. So everything it's starting to get connected. All right. So let's do another example. Find the curl of a vector field given by f xy squared z to the 4 comma 2x squared y plus z comma y cubed z to the c squared. Yes, c squared. And well, they're asking us whether this vector is conservative or not. All right. Well, is the curl? The question is the curl of a vector field a scalar or a vector field? Well, we'll find out when we get the answer to this. In the meantime, let's see. So curl F, which is nabla cross F, that is, let me write the xy squared z to the 4th, 2x squared y plus z, and y cubed z to the 2nd, that's I, j, and k, and partial with respect x, partial with respect y, partial with respect z. All right. Again, I'm going to use the compact version in this case. So let's find the partial of h with respect to y. So the partial of h with respect to y, that's that's actually, well, I'm going to go here because I'm not going to have enough space over there. And that's going to be 3y squared z squared minus the partial of g with respect to z. So g is the second one with respect to z. That's just 1 minus 1. Well, just looking at the first component, which is not a 0, we can already tell that the vector field is not conservative, right? But of course, we still need to find the curl. minus, okay, in this case is the partial of h with respect to x. So that is, well, 0. There's no x's at all. Minus the partial of f with respect to z. That's 4x y squared. Z, 4 minus 1, that's 3. That's in the direction of j. And finally, plus the partial of g with respect to x, which in this case is 4xy minus partial of f with respect to y, that's 2x y z to the fourth. That in the direction of k. All right? And that's the curl. Yes?
Can you highlight what the H?
Yes, I'm going to do that.
Just so I can.
Sure. So this is h with respect to y. This is g with respect to z. And this is h with respect to x. And this whole thing is going to be f with respect to z. And g with respect to x.
Okay. I was talking about like at the beginning.
The I, the j, and the k. What do you mean?
Yeah, like what's H by itself?
Oh, yeah, I see. So that's f,
Okay, that's what I was.
that's g, and that's h. But still, I think it helps to get these other subscripts as well, right? Just for reference. And it's fine. Well, I wouldn't expect that you write them on the exam or something. That's fine. And just as long as I see the correct work, it's fine. So the question here is it conservative? Yes or no? No, we didn't get the zero vector, so not conservative. And well, is the curl a vector field or a scalar function? Which one is it? Vector field, right?
Aren't they always vector?
Yeah, because in this case we have this ij's in case that's a vector because the cross product gives us another vector. Then in that sense the curl is defined by a cross product. If we were asked the same questions about the divergence, well, in that case it's a scalar. All right. There's a lot more that we can do about this divergence. There's a lot of combinations of these operators, and well, the one that stands out the most is that of the divergence and when we relate the divergence and the curl. So we have a couple of functions. Well, this should have been an angular parenthesis or bracket. Fg, oh, I'm missing an F. Okay, there's a little typo here. So this should have been big F. That's F, G, H. I will fix it later. And both having the continuous partial derivative. Oh, I'm missing a space as well. Anyway, so here is the thing. When we have a vector field, F, and we have this nabla operator to perform the cross product, and then we do the dot on top of that, we do the dot product with the nabla operator again. Well, we're going to get the zero. We're going to get zero in this case. Well, in other words, the divergence of the curl, that is divergence of curl equals 0. And this 0, there's a lot more of this combination. These are going to be some identities or theorems that you will use a lot in advanced mechanics in physics or classical and quantum mechanics. You use this a lot. And let's prove this one. And well, number one, we're going to do the inside first, the curl. The curl of F, which is nabla cross F, that is I, J, K. And that's the partial of f. I mean, not of f, just a partial with respect x, partial with respect y, and partial with respect z. And we have the other row, which is f, g, and h. And well, we're going to use the same definition. I mean, there's really nothing numerical. Let's just copy that. So that's essentially h, y minus g, z in the direction of I minus hx minus fz in the direction of j, and plus g sub x minus f sub y in the direction of k. So that's the curl, all right? So that's the curl. Now we're going to take the divergence of this curl. That is div curl. In other words, we're going to double nabla this first as a cross and second as a dot. And well, essentially, we're going to do the dot product between the nabla operator, which is partial with respect x, comma, partial with respect y, comma, partial with respect z, dotted, it's a dot product with this huge result we got here. But I'm going to go to the other notation, the component notation, not a linear combination ijk notation. So h, y minus g, z, and comma, negative h sub x, and careful with the signs, plus f z, because this negative is getting distributed for both terms, and gx minus fy. All right, let me get some highlighters here so we can relate. Okay, so we are going to take the partial derivative with respect x of this first component, all right? Now, what's the partial? So essentially we have some function h for which we already took a first partial derivative with respect to y. Now, when we have this operator, that means second partial derivative, in this case h sub y, and then we're doing with respect x, and then minus g, take the second partial derivative of g. Well, we already did it with respect to z in the previous curl operation. Now we do it with respect to x. And then minus, all right, careful, let me use a different highlighter. So now everything with respect to y for the second component of the curl vector. And that's the partial of negative h with respect to x first, but now with respect to y. So that is hxy, and the partial derivative of the function f, for which we already took it with respect to z, and now we do it with respect to y. And last but not least, using a different color here, let the partial derivative with respect to z act on the third component of the vector field obtained by taking the curl of it. And so that's going to be, okay, the partial of g first with respect to x, then with respect to z, minus the partial of f first with respect to y, then with respect to z. Is this going to be 0? Well, check this out. What do we have over here? Let me use different highlighters this time. Well, I'm just going to underline so it doesn't get confused with. So let's look at the f's. F first with respect to z, then with respect to y, and then we have negative f first with respect to y, and then with respect to z. We have them in reverse order. Do you guys remember a pretty cool result of the mixed partial derivatives? Isn't it the same? The second partial in the reverse order, the same In other words, aren't these two really the same? Because of the mixed partials, so we can already cancel this out. In the same way, we can also check for G, Zx, Xz, mixed partials, they're the same thing, cancel. For H, same thing, Xy, Yx, they're the same thing by mixed partials. What did we get in the end? 0. All right. Yep. I think there's a little bit more. There's one more page here. Another theorem. That's the product rule between when we're multiplying a scalar function with a vector field. So essentially, it's like finding the derivative, but in this case by means of the nabla operator, which is this set of either 2 or 3, depending on whether we are in R2 or R3. So the derivative of the product is the derivative of the first, that is nabla of the first times f, plus the second times the derivative of the first. But in this case, that derivative is given by the nabla operator. So that's another pretty cool result. And the last result over here is that the curl of nabla phi equals the zero vector. All right, where have we seen this phi before? Remember that phi, we use it to label a potential function, a function whose gradient is the given vector field. But what happens when we, in other words, this potential function tells us that the derivative, which is a vector field, it's a conservative vector field. And what's the curl of a conservative vector field again? Seen it, the zero vector, which is like the alternative way to determine whether a vector field is what's it called? It's conservative. I see there's another page, but there's nothing in the last page, right? All right.